Ever feel like the problems we're trying to solve are getting kind of, well, almost too big for our computers?
Yeah.
Like I'm talking about modeling climate change like down to every cloud and every gust of wind, or
Right.
designing new medicines at the molecular level.
Yeah.
That's where quantum computing comes in.
It's
And just to be clear, right off the bat, we're not talking about just a speed upgrade here.
No.
This is a totally new way of thinking about how we solve problems.
It really is kind of a fundamental shift. It's a bit like the difference between like counting on your fingers and then suddenly inventing, advanced calculus.
Right.
We've pushed classical computers pretty far.
Yeah.
But, some tasks are just too enormous, too complex for their basic design.
Right. It's like we're trying to map a whole galaxy using nothing but a ruler. We need a whole new set of tools, and those tools lie in the quantum realm.
Yeah.
But before we journey too deep,
Right.
let's do a really quick recap of how our everyday computers work.
Sure.
They use bits, which are basically just tiny switches that can be either on or off, representing 1 or 0.
Yep.
And for decades, that's worked remarkably well.
It has. It's taken us a long way.
But when you're trying to simulate the interactions of billions of atoms in a molecule, or factor a number with millions of digits, which you need to do to break modern encryption,
Right.
those simple on or off switches, they
hit a wall.
hit a wall hard.
They do.
So how does quantum computing change the game?
Well, this is where things get...
This is the good stuff.
This is where it gets really interesting. Instead of a bit, we have something called a qubit.
Okay.
And instead of just being on or off a qubit, can be in a state called superposition. Superposition. And it's kind of a tricky concept. But one way to think about it is to imagine a coin spinning in the air.
Okay.
It's not heads, it's not tails, it's both at the same time.
Until
it lands, right?
Yeah.
That's kind of what a qubit is like.
Interesting.
It holds the potential for both 0 and 1 simultaneously, and it's only when we measure it that it collapses into a definite state.
Huh. So it's like it's holding both possibilities at the same time until we force it to choose.
Exactly. And this both at once quality is what gives quantum computers a huge advantage for certain types of problems.
Okay, so we've got these qubits spinning like tiny possibility-filled coins.
I like that. Yeah.
Cool, but how do they work together?
Oh, wow.
How do they talk to each other?
This is where things get really wild.
Oh, okay.
And we get to another really important concept called entanglement. Entanglement. So imagine 2 of those spinning coins.
Okay, 2 coins spinning.
But here's the catch. If one lands on heads, the other one instantly snaps to tails no matter how far apart they are.
Whoa, wait.
That's entanglement.
That's crazy.
It is crazy. It's like they have this invisible connection.
So these qubits are linked, influencing each other instantaneously.
Yeah, you got it. And that interconnectedness, that ability to influence each other in this bizarre quantum way is what gives quantum computers their real edge.
It's not just the individual qubits, it's how they're all linked together.
Exactly. It's the relationships that unlock the true power of quantum computation.
It's like they have a secret language.
Kind of, yeah, like a way of communicating instantly across vast distances.
This is blowing my mind. Okay, so we've got these entangled qubits working their magic, but why should we even care?
Right.
It sounds fascinating in theory, but how does it actually translate to real-world problems?
That's the really exciting part, right?
Yeah.
So let's take cryptography, for example. How much we rely on complex codes to protect our online data, financial transactions, all that.
Right.
Well, those codes are built on math problems that are really, really hard for even the best classical computers to crack.
Right, like finding the prime factors of a ridiculously huge number.
Exactly. And we're talking it would take years, decades, even centuries for a classical computer to brute force its way through that.
Yeah.
But a quantum computer running what's called Shor's algorithm could theoretically break those codes in a fraction of the time.
Whoa.
It'd be like having a master key to the internet.
That is both exhilarating and terrifying at the same time.
Yeah, a little bit of both.
So cybersecurity is definitely in for a wild ride as this technology keeps developing.
Absolutely.
What about drug discovery? You mentioned that earlier.
Yeah, our sources were really buzzing about that one.
Yeah.
So designing new medicines often involves simulating how molecules interact, which gets incredibly complex.
Right.
Classical computers just really struggle because even a small molecule has so many electrons interacting in so many ways.
Okay.
It's kind of like trying to predict the weather patterns of a hurricane using like a child's paper airplane.
Okay, I'm getting that analogy.
So where do qubits fit in? Well, they can simulate those molecular interactions much more accurately and efficiently.
Interesting.
There's a type of algorithm called a variational quantum eigensolver.
Catchy name.
Yeah, VQE for short.
Okay.
That's showing a lot of promise for this kind of thing.
So we're talking about potentially designing drugs tailored to an individual's specific genetic makeup.
Exactly.
Or even developing entirely new treatments for diseases like Alzheimer's that we just haven't been able to figure out yet.
It's a really powerful tool for that.
That's what I call progress.
Yeah.
Speaking of complex systems, what about climate change?
Ah, yes, the big
We're talking about a problem with countless variables, right? Everything from ocean currents to volcanic eruptions.
Oh, and don't forget the clouds.
Oh, yeah. The clouds are a big one.
Even with today's supercomputers, simulating cloud formation accurately is a huge challenge.
Really?
Oh, yeah, and clouds play a massive role in regulating Earth's temperature.
So if we could get more accurate climate models, that would mean better predictions and more informed decisions about how to address this whole climate change thing.
Precisely, quantum computers could let us create models that are significantly more accurate and much more detailed.
Wow.
Imagine being able to pinpoint which mitigation strategies would actually have the biggest impact.
Yeah.
Or predict regional climate shifts with much greater certainty.
Yeah.
It could revolutionize our whole understanding of the planet.
It's incredible to think about.
It really is.
So we've covered cryptography, drug discovery, climate modeling. It seems like there's no problem too big or too complex for quantum computing.
Right. The possibilities seem almost endless.
What about artificial intelligence?
Oh, yeah. AI is going to be huge.
I feel like AI is already everywhere. I mean, how will quantum computing impact that?
Well, AI relies on algorithms, right?
Right.
Quantum computers can supercharge those algorithms, making them exponentially faster and much more powerful.
So we're talking about an AI revolution on top of a quantum computing revolution.
That's a good way to put it.
What kind of real-world impact could we see from that?
Well, think about medical diagnoses, for example. A quantum-enhanced AI could analyze medical images with far greater accuracy than any human doctor.
Wow.
Potentially catching diseases much earlier and saving countless lives.
Wow.
Or imagine personalized learning plans that adapt to a student's strengths and weaknesses in real time.
Oh, that would be amazing.
Unlocking their full potential. And remember when we talked about Google achieving quantum supremacy?
Right, that was a big deal.
It was a huge milestone.
But for those of us who aren't quantum physicists, what does it actually mean?
Well, in essence, Google demonstrated that their quantum computer could solve a specific mathematical problem exponentially faster than even the most powerful classical computer available.
Oh, wow.
It was a benchmark achievement proving that quantum computers can outperform classical computers in certain areas.
That's incredible.
It was a big deal.
It sounds like there's still a long way to go before this technology is widely available, though, right?
Absolutely. And it's not just Google making strides. Companies like IBM are working hard to make quantum computing more accessible. They're building platforms and partnerships that allow researchers and developers to actually experiment with quantum algorithms and explore real-world applications.
So it's not just about building bigger and better quantum computers. It's about making them usable and accessible to a wider audience.
Exactly. It's about democratizing access to this powerful technology so that we can actually unlock its full potential.
Oh, like that.
IBM's goal of creating a 1,000 qubit computer by 2025 is incredibly ambitious.
Yeah.
But if they succeed, it could be a complete game changer. Imagine the possibilities if we could harness that kind of computational power for good.
Oh, okay. So we've covered so much ground here.
We really have.
From breaking codes like it's nothing
to
completely revolutionizing medicine. And even tackling climate change.
Yeah.
It seems like quantum computing could seriously reshape the world as we know it.
It really does have that potential.
But, you know, it almost sounds too good to be true.
Yeah, I can see why you'd say that.
Are there any downsides? What are the challenges in actually making all of this a reality?
That's a really good question. And it's important to remember that we're still in early stages here. Right. It's a bit like the early days of flight, you know? We knew planes could soar.
Yeah.
But there were a lot of kinks to work out first.
So what are the biggest hurdles facing quantum computing right now?
Well, one of the biggest ones is the sheer fragility of these qubits.
Right.
Remember how we talked about superposition and entanglement?
Yeah, those delicate states that give the qubits their power.
Exactly. Even the tiniest disturbance.
Okay.
Like a vibration, a change in temperature, even a stray photon.
Wow. Can cause a qubit to lose its quantum state. and that leads to errors in the calculations.
So it's like they're holding this thought bubble that could pop at any second.
That's a good way to put it, yeah.
So how do they even keep these qubits stable long enough to actually do anything useful?
It requires some incredibly precise engineering.
Okay.
And some seriously cool technology.
Okay.
Literally.
Literally.
A lot of these quantum computers need to be kept at temperatures that are colder than outer space.
What?
It's just a hair's breadth above absolute zero.
Wow, are you serious? That's insane.
It's pretty wild. And even then, maintaining those conditions for long periods is really difficult and crazy expensive.
Yeah, I bet.
And on top of all that, we're still figuring out how to write effective algorithms that can actually take advantage of these really quirky quantum properties.
Oh. It's almost like we're trying to write a symphony, but for an orchestra of instruments that we're still learning how to play.
It sounds like a monumental task.
It is,
but hearing about all the potential benefits, it feels like these challenges are worth tackling.
Oh, absolutely.
This isn't just like a technological leap. This is a fundamental shift in how we approach knowledge and problem solving.
That's a great way to put it. It really is a completely new way of interacting with information with the universe itself.
Well said, and it's been amazing to delve into this world with you today.
It's been fun.
And to our listener, thank you so much for joining us on this deep dive into the quantum realm. We've only scratched the surface of this incredible technology, but hopefully you've come away with a sense of its mind-blowing potential and those daunting but exciting challenges that lie ahead.
I think so.
And if this has piqued your curiosity, we encourage you to keep exploring. Who knows, maybe one day you'll be the one writing the next chapter in the quantum revolution. Until next time, keep asking questions, keep learning, and keep diving deep.